Okay, so if you still remember what we have discussed from chapter 1 until chapter 4, we have discussed mainly about particles and how they move. And the thing about particles, it's a point, so you have only one direction, and then of course you can define it whether it's a normal direction or tangent direction if it's on a curve, right? We have not discussed what happens if that body of interest that we are interested in is moving in an angular motion. So let's try to try to discuss about what happens with angular motion. A point having no dimension, because a point is just a point, right? It cannot have angular motion. If it spins in its place, like I mentioned before. So only lines or bodies can undergo angular motion. For example, if you look here, so for example, imagine this is your plane of movement, moving. Well, let's say imagine like this is a paper, and then you have a line that we call R. This line can move around a reference. I'm sorry, the rotation axis that goes through O, right? So you have this angular motion of R, and we can define the position of this movement by measuring the angle between a fixed reference, and you can just pick one, any fixed reference, and then measure the angle to our line R. So this is how we define our angular position lah. So imagine if have a point here P on this our line R, and then there is a change in the angular position from here to here. So this is where you have your angular displacement, meaning there's a change in the position, and we call it as the d theta. So the d theta has a magnitude which can be degree or radian or revolutions, and of course I hope you still remember that one revolution is equal to 2 pi radian, equal to 360 degrees. Since motion, we always refer our motion is about a fixed axis, so the direction of the d theta is always along this axis, and usually we will define our displacement by the right hand rule. So imagine you hold your right hand like this, so a movement in this direction is your positive. So in this case, and we also define our direction of our angular displacement as pointing upwards in two dimension. By, if for example, if you look like here, if both the position, the angle, and the angular displacement are counterclockwise, so the thumb will be pointing upward from the page. So as a summary, even though the direction of rotation is in this direction, we say that the direction of angular displacement will be in this direction according to your right hand rule. Okay, so don't confuse the direction of rotation, which is you can define by clockwise or anti-clockwise, with the direction of the angular displacement. Okay, so you have your angular displacement. Then what about angular velocity? So angular velocity, you have your angular displacement. If you derive with time, you will have what you call your angular velocity, which usually we put as omega lah. And usually it has a magnitude where we put as radian per second instead of degrees, because this will make it much easier for you to do a lot of things later lah. So the direction of this angular velocity is also the same as your angular displacement, which is depends on your right hand rule. So the direction of angular velocity is along the axis of rotation. Okay. So usually we refer to counterclockwise rotation as your positive lah, just like your hand here. And lastly, for angular acceleration, you derive your angular velocity with time, and you will get your angular acceleration, usually represented by alpha. We can represent as the single derivative of your angular velocity, or you do your double derivative of your angular displacement. And similarly, the line of action is similar to your angular velocity and also your angular displacement. However, the direction up or down depends on your angular velocity. Is it increasing or decreasing? If your rate of change of your angular velocity is decreasing, meaning it becomes smaller and smaller, and alpha is called an angular acceleration, and its direction will be opposite, meaning if the angular velocity is upwards, then your angular acceleration will be downwards. If your angular velocity rate of change is increasing, meaning it's become bigger and bigger, then your alpha, your angular acceleration, will have the same direction with your angular velocity and angular displacement, and can eliminate your dt to get your equation here, which you get from, as you know, that the angular acceleration is rate of change of the angular velocity, and you know the angular velocity is equal to rate of change of the angular displacement. And if you find dt for both of these, you should get the equation d omega over alpha is equal to d theta over omega. And if you rearrange, you will get this, right? Alpha times d theta equal to omega times d omega. So it means that you can see a lot of similarities actually with our linear kinematics. So for your linear kinematics, you still remember your equations: v equal v theta plus at, and then you have your s equal s theta plus v initial v times t plus 1 over 2 constant acceleration t to the power of 2, and also v to the power of 2 is equal to initial velocity to the power of 2 plus 2ac. I'm sorry, c should not be bigger. Your constant acceleration is equal to s minus s theta. So it's quite similar. The only difference being you replace your v with omega, your angular velocity. You displace your displacement with your angular displacement, and you replace your acceleration, constant acceleration, with constant angular acceleration.